Hello, I'm Robert Toomey, a research developer working at the Cooperative Institute for Severe and High Impact Weather Research and Operations. Today I'm going to talk in detail about one of our largest, most used algorithms in research and now in operational deployment. I'll cover how we use multiple radars to create the giant detailed weather images that cover the continental US and more. If you bear with me, I promise you'll learn a couple of things about the merger and CONUS generation process that you didn't know before. In particular, I'm going to talk about the technical details involved and experimental new code attempting to improve upon the process. So, meteorologists, bear with me, but first, let's talk about the data we're dealing with. Basically, we have a giant network of WSR-88D radars that cover the US, and we also have other contributing radars from other areas such as Canada. Each of these radars has an independent, real-time stream of data. For the layman, these are rotating spinning radars that scan at a particular elevation angle, then after scanning 360 degrees in a circle, they change the angle and do another scan. These basically form a cone shape in space and time that bends some due to refraction of the radar signal in the atmosphere. The collection of cones and elevation angles for a radar is called a volume coverage pattern, or VCP for short. To make this more clear, here's a picture of a VCP pattern. Typically, they have a named identification number such as 12 that refers to the set of angle degree numbers that make up the pattern. This data is polar coordinate in nature, and to merge it with other overlapping polar radars, we have to spend a lot of time with CPU and math to calculate and interpolate the data between the angles. Another big part of this process involves converting from polar to Cartesian coordinates using GIS formulas. In our current process, we have three major stages involved. In the first, we convert data from the polar azimuth and range to Cartesian grid coordinates. The azimuth angle we use matches GIS bearing, where 0 is north and east is 90 degrees. Range is the distance traveling along the elevation from the radar outwards. X is mapped to a longitudinal coordinate and Y to latitude. The Z coordinate is height, which tends to not be uniform. In other words, we might want our 3D output to be more dense at different height values. Terrain plays an important role with radars, since the beam blockage can be fairly complicated. This involves digital elevation model data and calculating a percentage of blockage based on the beam and the height of the surrounding terrain. In the second stage, the time window of the data is important, so that old data expires, and we also need to have low latency of this data due to the nature of radar data usability. Finally, in the last stage, we also run various algorithms on the final global merged Cartesian data grid. These are algorithms such as ecotop, which calculates new values based upon a vertical column of the final Cartesian grid. Our current code for doing all three stages is called W2merger. It was designed around 2006 and thus with older CPU and RAM capabilities. This automatically led into the creation of a global disk cache of mathematical calculations. With the technology of that time, there really wasn't a choice. However, there is a lot of overhead involved in this. Special tools are used to pre-create caches and decide on the number of radars contributing values to a point. W2merger also needs radar VCP info in advance for guessing data expiration times, but this is becoming more difficult with radars that are changing VCPs unpredictably. It will also have issues with new technologies such as phased array, where VCP makes less sense. W2merger also tries to do this with a monolithic single algorithm that does too much in one program, which could benefit by breaking up more cleanly. The first refactor attempt is to create an optimized stage 1 that uses modern C++ and divides the caches up more efficiently. The lowest level of horizontal scaling that is probably reasonable for our use case is to process a single radar in a single moment, such as reflectivity. Dividing lower than this is probably not realistic, so this represents the smallest node of data processing, at least for stage 1 of merger. With modern CPU and RAM, we can try to put more work onto a radar node. More available RAM in modern systems means we can store more caching in memory for speed. It also means we can calculate more on the fly if necessary, which will simplify the use of the algorithm. This shifts more information to stage 1 and allows us to pass sparse data to stage 2. We also want to use virtual volumes versus static VCP angles. So now, we will discuss all the details involved in the process. This may be obvious, but the very first thing we need to do is inset the global coverage grid to the area of the radar. Given a radar range such as 460 kilometers, we can use the Great Circle ground distance to create a bounding box within the larger coverage of all the radars. Here I'm showing a 460 kilometer circle around the Oklahoma KTLX radar. This cookie cutting reduces the computation time and caches sizes for that radar. However, we keep the box coordinates based upon the larger global coverage grid. You can think of it as a piece of graph paper where you have aligned and drawn a smaller box using the squares. So now we can talk about, with more RAM and CPU, how we're able to handle caching better. With billions of points, trigonometric functions are slow, so strategically caching sine, cosine, and other values can drastically speed up the operations that we need to do. The first thing we do is we cache the sine and cosine of the Great Circle distance to attenuation ratio. And the second thing we do is we cache the azimuth range and elevation per grid point. We also cache the terrain percent blockage per grid point. All of these values can be used during the computation loop. We store a value for each 3D point, except for the sine cosine, which is just 2D of the radar coverage grid area. For the current merger, it's taking a startup time of under a minute and around 3.2 gigabytes of RAM, and possibly this could be written to disk, but this is probably not necessary. So let's cover each of these caches in a bit more detail, since I quickly talked about them on the last slide. The Great Circle distance cache stores the sine and cosine of the angular distance ratio between the Great Circle distance and the attenuation angle. We first calculate IR, which is 4/3 of the Earth's radius, and also the Great Circle distance from the radar center to the grid point. Then we store the sine of GCD divided by IR and cosine of GCD divided by IR. We then use these values to help create two other caches. The first one is the azimuth range elevation cache that is generated on startup, so this helps with startup cache generation. The second one, later on, is during the main computational loop to calculate the range and height of the interpolated data value. The azimuth range elevation cache is another lookup that is created on startup. It uses the Great Circle distance cache that we just mentioned from number 1. Basically, since we have to iterate through a XYZ cube, where each point has a latitude, longitude, and height, we need to quickly get the polar values for that radar for each point. This is what this cache is used for. It uses the stored sine cosine cache, and it uses refraction formulas to do the curvature based on the atmosphere, which we'll show later. A third cache we calculate on startup is the terrain blockage percentage cache. This requires reading in a digital elevation model or DEM file for a radar coverage area and then generating the percentage of blockage values for each 3D grid point. The nice thing is that this fits into a single character for a 0 to 100% blockage value, though we could up this to float level precision if we wanted to. The terrain in W2merger and the fusion algorithms skip points where the terrain blockage is over 50%, which helps cut down on computations at lower elevations. Our QC algorithm applies terrain filtering for windmills, etc., so I suspect we've always used terrain in merger just to reduce the number of point calculations, but we do have this value and we can use it as we want. W2merger typically uses the terrain algorithm to filter block calculate data past a 50% blockage amount, like I said. So one problem found during experiments with the current code was that if the coverage of the DEM given to the radar is smaller than the radar range, this gave a false square where points outside the DEM coverage were not blocked. Another issue was the assumption of negative elevation blockage, which can be seen in the circle at the left image. Basically, once the elevation goes negative, you get a automatic complete blockage. The original assumption of W2merger is that elevation angles can't be negative, which changes now, say with Canada radar inputs, where you have negative scan angles. After modifying the algorithm slightly, here is a corrected image where at 460 kilometers, we handle the negative angles and we have over 50% blockage along a direction. However, we do actually calculate all the percentages in case we wanted to use terrain in a more complicated way in stage 2. That covers the initial startup cache generations per output layer. However, we have running caches that must update while computing and when receiving new tilt data. There are 4 important running caches. The virtual volume cache holds the radial polar data for each elevation, and the radial set lookup cache calculates the azimuth range to array index. The CAPI latitude longitude grid cache can hold previously calculated values to help with sparse output calculations. Finally, the upper lower tilt cache allows us to skip calculations that do not change from previous incoming tilts. We will have to explain each of these in more detail. The virtual elevation cache stores the current set of elevation angles within the time window of the algorithm. For lookup, they need to be sorted, and they have to refer to the radial set 2D data of the elevation scan. Since data is in space and time, elevation angles replace the matching older angle. Also, since VCP patterns can change, the angles have to expire at some point if they get too old, because another angle to replace it might never actually come. Searching is done linearly for small n, where we find the angle below and above the angle searched for. This is actually, for small n, it's actually faster than binary search, which was interesting. These 2D data sets are typically small versus the grid of the merger. A typical radial elevation might be 360 degrees by 460 or 720 gates along each radial. Now, the radial set lookup cache is a function that maps from the azimuth and range to the actual index coordinates in the 2D array of the data. This has to be created during runtime for every new tilt that comes in. This requires the azimuth and range to be calculated in 3D using refraction to get the range values correct. However, once calculated, it is a linear lookup. Here you can see an example of how a radial set of data would map to the 2D table of the array data. And you'll see the values in the circle where the gates are shown, and then the corresponding table on the right, which is actually a 2D lookup, which doesn't have that spatial information. The lat-long grid cache serves to store the latest calculated value for each layer of the virtual volume. It represents a CAPI at each of the layers of the merger. Here is an example from the KTLX radar where we can see a slight ring effect from the multiple elevations contributing vertically to the value of the CAPI layer. We can output these layers if we want to see a mini cube of the output values for that radar. However, we only send the sparse value changes to stage 2. Otherwise, that stage will be overwhelmed. The upper lower tilt cache allows us to skip recalculation of values where one of the surrounding radar tilts is not changed. Basically, we can do 2 cheap pointer checks for data above and below and only change output when that tilt changes or expires. So imagine a state on the left that has been fully calculated. You can see 1, 2, 3, 4 tilts. Everything, the green represents data that's been calculated. If the top tilt changes, you only need to recalculate the values between that top tilt and the one below it, so the area in red. And if you have an expired tilt, say the second tilt up from the bottom expires, you would now have to calculate that area. This reduces the amount of calculation that has to be done whenever an incoming tilt comes in. So after caching, we now have the main computational loop. When a new elevation radial set is ingested, we generate and cache the radial set lookup cache for that elevation. We also update the volume elevation cache and replace that elevation and purge data outside the valid time window. We then iterate over the final cube. We have the values from the great circle distance sine and cosine cache, and we have the azimuth range elevation and terrain cached values. If the points are outside the radar range or completely terrain blocked, 50% or whatever rule we set, they can be skipped. We search above and below elevations in our virtual volume. If the current above and below elevations are exactly the same for a location with the same times in case the angle is replaced, then calculating the new value can be skipped. We can use the lat-long grid cache in this case. Otherwise, we use the sine and cosine cache along with the tangent and cosine of that particular tilt to get the range and height of the final calculated value. The interpolation process usually involves quickly finding the elevation above and below the point of interest. Using these true elevations, we have actual data values and the cached range and height for them. For the middle value, we can calculate the range and height and value based on linear interpolation. We can use the beam width of the tilt for cases where only one tilt is available or a tilt has missing data. For the first pass, we've used simple interpolation for proof of concept, but this math still needs to be tweaked to take into account the thickness of the beam and other factors. This shouldn't affect the speed or caching, so it will be worked on as the algorithm is tested. As a counterexample, W2merger's interpolation process involves weighting the data exponentially when closer to the actual beam width. So it appears to be a polar degree interpolation versus true vertical. And the question is, which is better? I would assume that mergers is better, and this is where we are going to go in the future. This exponential interpolation, the weight is 0.005 at beam width, 1 at the center, and 0.5 at half beam width. And you can see the linear line, the straight line in this graph would represent actual true linear interpolation, and the curved section would represent the exponential interpolation. If you mirror this, you can also see how, as you go from one tilt to another, how it's symmetrical. The raw files for stage 2. Raw files only need to output the sparse changes caused by two things. Like we said, 1, the 3D points affected by new incoming tilt, and the 3D points affected by any expiring data. And basically, this means that once an incoming tilt is processed, the output sent to stage 2 is massively reduced. So higher CAPI levels tend to have more points but less data. Lower CAPI levels have more terrain skip points, more valid data values. An incoming tilt can actually change 0 points in certain layers, and we optimize on all of this. Anywhere from 0.01 seconds a layer to 0.5 seconds a layer is currently how it goes. So for a 33 layer processing, we're looking at 10 seconds. It's actually fairly quick. The time involved is in the startup time pre-creating the caches. So the action list now is, there's a few things here. We want to display the lat-long grids for the output of one or more stage mergers. We need to debug, tweak, and mess with the interpolation more to get it to align more with merger. We need to make sure things are spatially in the right locations, that there's no errors. So there's bound to be little bugs and things that always happen in this type of thing that need to be tweaked. So we need to get this on the web display so we can compare. This may want us to use the MRMS binary directly, or we can use lat-long grids and they can be converted to binary and displayed. We also want to start ingesting the raw files into a larger stage 2 merger and compare outputs. In theory, the current stage 2 should have no issues with the reduced points passed, but a new stage 1. Current stage 2 also purges data, but it won't matter if we purge it first. And how to get this, what to do it. You have the MRMS 20 flag, C++ 11 and newer OS, and you get clone. That's the RAPIO library. This is the new engine that I'm using for this that can be used, but it will be built into MRMS 20. And have a good day. I hope you learned something.